Hello, learners. Welcome back to Top Notch Online TV, the ocean of knowledge. Today, you're going to be with me, teacher Thaddeus Mbaluka, the ocean of chemistry, and a certified working chemical. In our today's lesson, I'll be able to navigate through a very important area in chemistry practical, and that's the area of graph work. With focus on energy changes graphs. This is the area with the very many types of graphs that are normally tested in KCSE. And you're likely going to interact with one of them. Remember, in 2022, there was no graph. So there is a high chance this year, 2023, we are likely going to face a graph. Graphs are always tested. So today, I'm going to focus on the graphs of energy changes. So let's start by looking at what is tested. As I've said, you always focus on what is tested, how it is tested, and what are the expectations of the examiner. So these important points, you need them. You're not going to find them in most of the publications. But we have important points that you require for you to be able to answer questions on graphs. So the first point that is very much important is, graphs, we start with the most important thing. Point number one is that all graphs of energy changes are two lines of best fit, each passing through two correct plots and must be extrapolated. All graphs of energy changes are two lines of best fit, each passing through two correct plots, and the two lines must be extrapolated. So what does that one tell you? There'll be no smooth curve in energy changes, and there is no graph whereby you're going to draw one line. It must be two lines of best fit. Each line must pass through two correct plots. Of course, the first line, as you're going to see later, must touch the first plot and extrapolated to intersect at a particular point. So the key word there is there must be two lines for energy changes, and each line just need to pass through to correct plot and must be extrapolated. That is point number one. Point number two is that the first line of best fit must touch the y-axis. So all graphs of thermochemistry, or rather energy changes, must be extrapolated. So it must touch the y-axis, meaning that the first plot, the first line that is originating from the y-axis must originate from the first plot. The graph of highest temperature against volume, that is point number three. The graph of highest temperature against volume, the y-axis must not start from zero, but y-axis must always start from zero. Remember, we are either going to plot a graph of temperature against time, temperature against volume. So the x-axis must start from zero because we always have the room temperature. So if we put water here, if we have put some water here, the starting point of the experiment is the room temperature. So if I have put some water here and I insert a thermometer, it follows automatically that now, when you're going to get the change in temperature, the starting point will be the room temperature. So that means that if you're plotting the graph of temperature against time, it must start from time zero. That is very much important. Let's look at another point. Another point that is very much important, that graphs that are derived from discontinuous data. Graphs derived from discontinuous data must be extrapolated and joined at the point where there is no data. I'd like to explain this point more using an example. So just hold on, keep it here. As you wait for me to explain that point, because I know some students are not getting that point of graph derived from discontinuous data. I'll be able to explain that. So another important point is that the extrapolated lines must never intersect on a plotted point. Remember, the two lines of best fit must be able to intersect. If there's a line and there's another line, they must be able to intersect. So where these lines intersect, it must never be on a plotted point. Again, I'll be able to explain the chemistry behind that. The graph of change in temperature against volume must start from 0, and the x-axis must also start from 0. So you can see, now if you are talking about change in temperature, at the beginning, the change in temperature is also 0, because the reaction has not started. The temperature will either rise or drop when the reaction is taking place. So at the beginning, if you are talking about the change in temperature, at time 0, the change in temperature is 0. So if a graph is plotting, we are plotting change in temperature against volume. That's when you're dealing with the neutralization reactions. Then both the y and x axis must start from 0. Let's now go and start looking at a real example. Let's look at this experiment. So here we are talking about, we're having volume of C added and temperature of the solution. So we have this kind of a table here, as you can be able to see. You're able to see there's a table here. We are having the volume, and we are again at the temperature. And we are adding a volume, maybe possibly to an acid at a base. So you are going to have volume of C added, and then we are measuring the temperature. So whereby you have not added any volume, like these are reaction. For example, assume these are reaction between sodium hydroxide and HCl. First of all, you start by putting sodium hydroxide in a beaker. Then you start adding hydrochloric acid little by little. So at the beginning, we have when you have not added any volume. So at that point, that's when you get the initial, rather the room temperature, which according to this is 22. Then as we continue adding more acid, the temperature is increasing up to the maximum, then it starts to decrease. In that kind of a scenario, I have to explain to you, wherever you're going to find a table like this, student, listen, there are only two options. If you're going to find a table like this one on the screen, if you're going to find a table drawn like this, of course, the column for temperature will not be filled. There are only two options. Either the temperature will increase to the maximum, then drop. Or the temperature will drop to the maximum, then start rising. Look at this now. Let me explain this, then I'll be able to explain why that the temperature increase then drop. In that kind of a scenario, look at that. The initial temperature is 22. And you can be able to see from my point, I have one line of best fit. And as I said, this line of best fit must originate from the y-axis, as you can be able to see. So another student could have picked the line starting from here. Of course, and you could even have passed through 2-3 plots. But this is wrong, because it must start from the first plot, which is now the room temperature. Remember, what you're having here, number 2, represents the room temperature. So that must be the starting point. Then any other point. Then we're having now the other line of best fit that is representing the temperature that is dropping. So in that kind of a scenario, assume a student picked this. A student picked this line here, these 2 plots here from the screen. Then they could have intersected here. But remember what I'm saying, that the lines must always intersect above. Look at the point number 2. The extrapolated line must never intersect on a plotted point, and the point of intersection must be above or below or the plotted point. Very key word there. So let's go back to the graph. So you can be able to see, once we extrapolate these 2 lines, they are meeting here. They are meeting above all the plotted points. Let me now explain the concept behind that. We always say that science is more practical and empirical than theoretical. Any statement you make must be supported by a practical, rather logical evidence. And that's what you mean when you say science is pragmatic. Now, whatever I am saying is this reaction is exothermic. So being exothermic, like for example, if you put hot water in this container, wherever a solution is placed in a room and the temperature of that solution is above the room temperature, it will start losing heat to the surrounding to go back, rather to retain to go back to the room temperature, rather to finally it will assume the room temperature, rather it will acquire the room temperature. So the temperature is rising, yes, but at the same time, the temperature is getting lost. So practically, we cannot be able to get the highest temperature in this kind of a scenario. Therefore, that is why you are supposed to extrapolate the two lines to get a higher temperature than what you have recorded in order to mitigate the errors caused by the loss of heat to the surrounding, in order to take care of those errors that occur because it is lost to the surrounding. That is the rationale of extrapolating graph of energy change to get a higher temperature than what is recorded. Very, very important. Why does the temperature rise then start dropping? Because when you start carrying out a reaction, the reaction have to proceed up to the end. Then it will start decreasing. The temperature will start dropping after the reaction is complete. The reactions are no longer reacting. No more it is being generated, but it is being lost. So the system starts losing it. And that's why the temperature rises, then drops. Very important. I think that is now very, very clear. Let's look at another example. We are also having the previous example was for exothermic. This one is for endothermic. As you can be able to see, the temperature has dropped. The temperature has dropped from 23 all the way to 70, then start rising from 19 all the way to 22. Of course, again, I said, if you get a table like that, there are only two options. The temperature drops to the minimum and rises again, or rather rises to the maximum, then drops again. So that kind of a scenario, as you can be able to see, this is just the same like the other one. So I don't need to explain a lot. Is that again, you're going to draw two lines of best fit. It must originate from the room temperature, then another plot, then another plot, then you extrapolate again. Then here we have two lines of best fit, again, another line of best fit. Then it's drawn, dropping, and then it must meet below, because this is endothermic, it must meet below the room temperature. Why? Go put some water in a glass in a fridge, or rather, remove any water from a fridge, put it in a container. What will happen to that? It's very cold. It starts to lose heat to the surrounding, until by the end of the day, it will have acquired the room temperature. So if you have a solution whose temperature is below the room temperature, the solution start gaining heat from the surrounding. And therefore, again, you cannot get the lowest temperature because the temperature is dropping because the reaction is exothermic. But at the same time, the system is also gaining it from surrounding. So in that kind of a scenario, that's why we also extrapolate it downwards to get a lower temperature in order to take care of that heat that has also been gained from the surrounding. That is the rationale of getting something like that. And I want to explain, by the way, maybe some student will want, like you can see, the table is given 2 marks, 3 marks. How do you get those 2 marks, 3 marks? One, there's a mark for complete table. There's a mark for complete. Have you completed the table? Yes. That's very key. That's very much important for you to understand. There's also another mark. There's another mark for accuracy. Accuracy, we consider the initial temperature. Like the initial temperature here is 23, plus or minus 2 of the school value, because your teacher will also do the same experiment. Then, also the examiner will also give you another, have a mark for trade. Oh, no, not have a mark. There's also another 1 mark for the trade. Trade is, we expect, like in case like this, the temperature to drop, then rise. Drop, rise. That is now the trade, 1 mark. So if for the previous one, if you are marking this one, there'll be 1 mark for complete table. Then, of course, let me repeat that. The marks are divided into 4. There is a mark for complete table. Then there is another mark for accuracy, which is full mark, which is given based on the initial temperature. Then there is, I have a mark for decimal place. For temperature, we give, I have a mark for decimal if it's given to a whole number or 1 decimal place. If 1 decimal place, it's either going to be a 0 or a 5. So you can say 22.5 or 22.0. The decimal place must be used consistently. So whatever I'm saying, there are 4 marking points there. Then trade. Trade is, like for this one, it is increasing, then dropping. That is the drop. That is the trade. So if another student, the temperature increases until the end, that student will not get the mark for trade. And of course, if you don't get the mark for trade, there is 0 chance of you getting the mark for the curve. Then you go for the curve. How do you score 3 marks from the graph? 1, I have a mark for labeled axis. Like a student has labeled temperature here, and has also labeled volume of solution C, have a mark. Then there's also another mark for scale. The scale means that now the student should cover half of both the y and x axis. Like for example, how many plots are here? You can be able to see on the y-axis, I've covered more than half. And on the x-axis, I've covered more than half of the grid. In that kind of a scenario, you score a half for the scale. Then there's another mark for plotting. All the points that are there, have you plotted them? Sometimes, either the point, like for this one, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. If the student correctly plots 8, then we give you a full mark for plot. Then we also have now the graph, the lines. The lines is whereby we are saying there must be 2 lines. Each passing through 2 corrected plots. That one already have a mark. Then on extrapolating to join above all the plot, then we give you another mark. So that's now for a scale, I have. For labeled axis, I have. Plotting 1 mark and the lines 1 mark. That's how you get it. Very clear. So as I said, for the table, there is a mark for complete table, a mark for accuracy, there is a mark for decimal place. I have a mark for decimal place, and I have a mark for trade. That's how you score the mark. And these are free marks. You don't need to have understood the math chemistry. You just need to know how do you draw this graph, and that's how you get it. Then that's another graph that is showing you how you need to talk about that. That's now how you are showing that. Just another graph of now temperature against volume, passing through corrected plot, extrapolated to get a higher temperature than what is recorded. Then now we have, the graph that we are saying, that are graph derived from discontinuous data. Look at this one. Graph derived from discontinuous data for temperature. Like we can see, these are kind of practicals whereby you'll be told to put a particular solution in a beaker. Then you start, like you put a solution in a beaker like this. Then you start, assume this is the thermometer. You start measuring the temperature of that solution after every minute without adding any other reagent. In that kind of a scenario, the temperature remains constant because there is no reaction taking place. Then you can see at minute 2, which can be shown here. At minute 2, that's now whereby we are adding the other solid or the other solution or the other reagent. At that point, you are not measuring any temperature. Then, at that point, the temperature will either increase or drop. So there are simple issues that can happen here. In this kind of a scenario, you can see the temperature has remained constant then it has started to increase. So what am I talking about? I've said these are what I was telling you from the notes that graphs derived to Kwapa, graphs derived from discontinuous data must be extrapolated and joined at the point where there is no data. So I'm saying, as you can be able to see here, the temperature at 0 is 20, a half is 20, at 1 minute is 20, at 1.5 is 20, at 2 minutes, there is no plot because that's when we mix the two reagents. So in that kind of a scenario, there is the discontinuous data for temperature. At that point, that's why we are saying the graph derived from discontinuous data, after plotting, you have to get two lines of best fit. Then you extrapolate the first line to touch the point where there is no data, that is minute 2. Then again, the other one, because there's also no plot at minute 2, you also extrapolate and you extend that line again to minute 2. Then you join. The two lines are joined at minute 2, where there is no data. Why? The theoretical assumptions is that we assume that when we mix the two reagents at min 2, there was instantaneous rate of reaction. So at the min 2, when the two substances were mixed, there was instantaneous rate of reaction. Instantaneous from the word instant. The particles reacted together completely at that minute. And therefore, if the particles reacted together completely at that minute, then when the reaction is complete, that is when you get the highest temperature. When the reaction is complete, that's when you get the highest temperature. So in that kind of a scenario, that is why we are getting the change in temperature at minute 2. So that's why we are getting that point. All the other rules of marking and awarding marks applies, like in the other one. Then we can also have this one, whereby this is another scenario whereby the temperature remains constant. The temperature remains constant. At minute 2, there is no plot. Then start to rise again up to the maximum, start to drop. So in many a time, many students will get confused and try to draw. They'll even try to add another line here. They may even try to draw another line here. Then they have 3 lines. But you go back to my note that the graph of energy changes must only be 2 lines of best fit and must give you the highest temperature. If you cannot have this line here, because you'll not be able to join them at the minute 2 and get the higher temperature. So you ignore the rising temperature, then you draw a straight line here, then you extrapolate it to minute 2, then the other one you also extrapolate it to minute 2, then you join the 2 lines at that minute 2, and from there you get the highest temperature. It is as simple as that. That is how you get those kind of things. So for this graph derived from discontinuous data, the temperature can remain constant, rise, drop. It can also have this kind of a scenario whereby the temperature remains constant, rises, then start dropping drastically. Or we can have another one, remain constant, drops, rises. Or can remain constant, drop to the minimum, rise again. That's very much important for the student to be able to understand. So we have come to the end of our lesson today. This summarizes the concept of energy changes graphs. Of course, not well captured in most of the publications, but for those who don't have it, you can also get the Demystifying Chemistry Practical Guide, whereby I've also tried to analyze those graphs. Many graphs, you can be able to look at them. And there are so many graphs that have been brought. Looking from the year 1995, looking for 201, looking for 204, looking for 207, 208, 2010, 2013, 2014, 2017, 2018. We have always been having the Thermochemistry graph, and you can be able to see it from the Demystifying Chemistry Practical Guide. So keep on following here, at Top Notch Online TV, whereby we continue dissecting, we continue illuminating the concept of chemistry, looking at the difficult areas. Comment on the like, comment, and tell me any other topic that you find is difficult and you want me to demystify. Until next time, bye-bye.